In today's world, there's a material that looks, feels, and even smells like genuine leather, but it doesn't come from cows, goats, or any animal at all. Instead, it comes straight out of factories, labs, and high-tech manufacturing plants. We call it synthetic leather, fear. But how is this incredible material actually made? How do we transform basic chemicals and textiles into something that mimics one of the oldest and most luxurious materials in human history? And why is synthetic leather such a massive, growing industry, supplying billions of shoes, furniture pieces, and car interiors every single year? In this video, we're going to take you deep inside the synthetic leather production industry. So, grab a seat because we're about to peel back the layers on how synthetic leather is manufactured at an industrial scale. Before we dive in, don't forget to subscribe to our channel and hit the notification bell so you won't miss our deep dives into the fascinating world of how the world's essential materials are made. Now, let's get started. The first wave of artificial leather appeared in the 1920s and 1930s, when PVC-based products began to replace genuine leather in military gear, bookbinding, and upholstery. After World War II, the technology spread worldwide, giving birth to the first large-scale synthetic leather industry. By the 1960s and 1970s, faux leather became mainstream. It was affordable, versatile, and mass-producible. Shoe companies embraced it for everyday footwear. Automakers used it to upholster seats at a fraction of the cost of real leather. Sports companies adopted it for balls and protective gear. Fashion houses, at first resistant, slowly began to experiment, especially as coatings and embossing improved to make synthetic leather nearly indistinguishable from the real thing. But that brings us to the most fascinating question of all. How is synthetic leather actually made? What happens inside a production plant, from the very first raw material to the final sheet of leather-like material? That's what we'll uncover in the next part. Synthetic leather isn't built from plastic alone. At its core, it needs a base material, usually a textile. Common backings include polyester, nylon, or cotton fabrics. The fabric is chosen based on the final application. Thick, durable textiles for car seats and furniture, light, flexible ones for fashion and apparel. These fabrics arrive in huge rolls, sometimes stretching hundreds of meters. Workers load them onto machines where they are cleaned, tensioned, and prepared to receive coatings. The purpose of the backing is simple. It gives synthetic leather strength, flexibility, and structure. Without it, the plastic layer would tear too easily. In the factory, technicians mix the polymer granules with plasticizers to make it flexible, stabilizers to resist heat and UV, and pigments for color. The result? A thick liquid or paste known as a polymer solution. This solution will soon be spread across the fabric to form the top layer of synthetic leather. Now it's time to merge fabric and polymer. The textile backing passes under a coating head, where the liquid polymer is spread evenly across its surface. In wet coating, solvents are applied and then evaporated in a heated chamber, leaving a smooth layer of PU on the fabric. In dry coating, the polymer is melted and directly applied, then cooled to solidify. The goal: create a uniform, smooth surface that will later be textured to look like leather. After coating, the material moves through long heated tunnels, sometimes over 50 meters in length. Inside, heat and airflow evaporate solvents and cure the polymer. What was once a sticky liquid now becomes a solid, durable surface. This stage is critical. If the temperature is too high, the polymer may blister. Too low, and the layer won't cure properly, leading to poor durability. This is where the magic happens. Raw coated fabric looks smooth and plastic-like, nothing like real leather. To transform it, factories use embossing rollers engraved with leather grain patterns. The sheet passes through heated steel rollers that press the texture deep into the surface. This step gives synthetic leather its authentic look and feel. Next, the material is refined for aesthetics and performance. Pigment coatings are sprayed or rolled on for exact color matching. Protective top coats are added to improve water resistance, UV protection, and scratch durability. Gloss or matte finishes are applied depending on design requirements. Factories can also adjust softness by controlling the polymer blend, creating either stiff industrial leather or buttery soft fashion leather. After embossing and finishing, the synthetic leather is cooled, inspected, and trimmed. Large sheets are cut into rolls. Each roll may be 30 to 100 meters long and over a meter wide. These rolls are then wrapped, labeled, and shipped to manufacturers around the world. Shoemakers, car companies, furniture brands, and fashion houses will use these rolls to create the products we see every day. No batch leaves the factory without testing. Only after passing these rigorous checks does synthetic leather reach the market. In just a few hours inside a factory, plain fabric and chemical polymers are transformed into something indistinguishable from natural leather, but more affordable, scalable, and versatile. Synthetic leather is more than just a material. It's the story of human ingenuity, from the challenge of limited animal hides to the creation of scalable, versatile alternatives. It's a story of fashion and function, science and society, ethics and innovation. If you found this journey into the world of synthetic leather fascinating, don't forget to hit that like button, share this video with a friend, and of course, subscribe to our channel for more mind-blowing stories about how everyday things are made. Your support helps us keep exploring the industries that shape our world. They're the only part of your car that touches the road. They endure heat, rain, gravel, and thousands of pounds of pressure, all while keeping you safe at 70 miles per hour. But have you ever wondered how a car tire is actually made? It's not just rubber and air. It's a sophisticated blend of chemistry, engineering, and precision machinery. In this video, we're going deep inside the factories where millions of tires are born every year. You'll see how rubber meets steel, heat, and science, until it becomes the round, black marvel rolling beneath your feet. Let's start with the basics. Natural rubber. Harvested from rubber trees in Southeast Asia, natural rubber provides the elasticity and flexibility that allows a tire to deform under pressure, then snap back into shape. It's essential for absorbing bumps, smoothing out the ride, and handling the constant flexing that happens as the tire rolls. Made from petroleum byproducts, synthetic rubbers like styrene butadiene rubber and butadiene rubber add durability, resistance to wear, and temperature stability. These rubbers help tires perform under extreme heat, cold, and heavy loads, conditions natural rubber alone couldn't handle. Carbon black. Ever wonder why tires are black? That's carbon black, a fine black powder made from burning hydrocarbons in low oxygen conditions. It's added to the rubber to make it stronger, tougher, and UV resistant, dramatically improving tire lifespan. And fabric tires need to be flexible, but they also need to hold their shape. That's where steel wires and textile fabrics come in. Steel cords give structure and puncture resistance, especially in the tread area. Textile plies, usually made from polyester or nylon, provide shape and reinforcement for the sidewalls and body. Chemical additives. A variety of chemical agents are blended in for fine-tuning. These include sulfur, which makes rubber molecules cross-link during vulcanization, antioxidants and antiozonants, which protect rubber from cracking, processing oils, which improve flexibility and workability. Once all the raw materials are ready, rubbers, carbon black, steel, fabric, and chemicals, it's time to start crafting the actual rubber compound that will become the body of the tire. And it all begins in a machine that looks like a giant steel blender on steroids, the Banbury mixer. Temperatures inside can reach over 150 degrees Celsius, 300 degrees Fahrenheit. At this stage, timing is everything. If the mix runs too hot or too long, the rubber can burn or lose its elasticity. Too cold or too short, and the ingredients won't bond properly. So operators monitor every variable: temperature, torque, pressure, and time, with pinpoint precision. Once the batch is complete, the hot rubber is discharged in thick slabs called strips or cakes. These are then passed through two roll mills, huge horizontal rollers that flatten the compound into wide sheets with uniform thickness. Different formulations are prepared depending on the final function. Some compounds are soft and sticky, for tread grip. Others are dense and airtight, for the inner liner. Some are flexible but strong, for sidewalls and shoulders. Each type of rubber is carefully tagged, stacked, and stored. First up, textile reinforcement. Thin cords made from polyester, nylon, or rayon are sandwiched between rubber sheets in a process called calendaring. These layers become the body plies of the tire, adding shape, flexibility, and impact resistance. Then comes the steel. High-tensile steel wires are braided together into wide belts. These belts are coated in brass for better bonding with rubber, then cut at precise angles to control how the tire flexes and grips the road. Steel belts resist punctures, reduce tread deformation, and help maintain stability at high speeds. At the very base, thick steel bead wires are wrapped into loops. These beads are what anchor the tire to the wheel rim and keep it from popping off under pressure. Together, the fabric and steel form an internal skeleton, a kind of reinforced frame that allows tires to be soft on the outside, but unyielding at their core. With all the components ready, rubber sheets, steel belts, textile plies, and bead wires, it's time to assemble the tire. This step is called green tire building, and it's where everything comes together, just not quite finished yet. The process happens on a rotating drum. Layer by layer, the tire is built from the inside out. It starts with the inner liner, a thin, airtight rubber sheet that holds air pressure. Then come the body plies, the flexible fabric layers that give the tire its shape. After that, steel bead wires are added on both edges to grip the rim. Next, sidewalls are applied, forming the tire's outer edge, followed by steel belts, laid flat across the top to reinforce the tread area. Finally, a thick rubber layer, the tread, is placed on top. This is what actually touches the road. Once assembled, the uncured tire, called a green tire, is pressed, stitched, and shaped. It looks like a real tire, but it's still soft and unusable. To become roadworthy, it needs one more thing: heat. The green tire may look finished, but it's still soft, unstable, and unusable. To become a real tire, it needs to go through one final transformation: vulcanization. In this process, the green tire is placed inside a large mold, shaped like the final product. The mold is lined with engraved patterns, which will form the tread and sidewall details. Then, a rubber bladder is inserted into the center of the tire and filled with hot steam or gas. As pressure builds, up to several hundred psi, it forces the tire outward against the mold walls. At the same time, the entire mold is heated to around 107 degrees, 340 degrees Fahrenheit. This activates a chemical process where sulfur cross-links the rubber molecules, making the material harder, more elastic, and permanently bonded. Within about 10 to 15 minutes, the tire emerges fully formed, with tread grooves, branding, and structural strength all locked in. Vulcanization is what makes the tire durable, springy, and able to withstand everything from highway speeds to potholes. Without it, a tire is just a pile of soft layers. Now, it's finally ready for inspection. Before any tire leaves the factory, it must pass a series of strict quality inspections, because safety depends on it. First, trained technicians check each tire by hand, feeling for bumps, bubbles, or defects in the tread and sidewall. Then, high-tech machines step in. X-rays scan for internal flaws. Laser systems check balance, roundness, and uniform thickness. Some tires are randomly selected for destructive testing, inflated until they burst, spun at high speeds, or exposed to extreme temperatures. These tests simulate real-world abuse: highways, heat waves, emergency braking. Only tires that meet every safety and performance standard, inside and out, are approved for use. The rest, rejected and recycled. Because in the world of auto safety, there's no such thing as close enough. Every tire must be perfect, from raw rubber and steel to heat, pressure, and precision. Every tire is a quiet masterpiece of engineering. It's easy to take them for granted, but without them, your car wouldn't grip the road, take a corner, or keep you safe in the rain. Next time you drive, remember, there's a lot more beneath your wheels than just black rubber. There's science, craftsmanship, and thousands of decisions that all lead to one goal: keeping you moving safely. If you enjoyed this behind-the-scenes look at how auto tires are made, don't forget to subscribe to our channel for more fascinating breakdowns of the things we use every day. Hit the bell so you never miss a new episode. Like this video if you learned something new, and let us know in the comments, what should we explore next? Thanks for watching. See you in the next one. Strong, flexible, and endlessly useful, rope has been a tool of civilization for thousands of years. But how are ropes made today, in high-tech factories at industrial scale? Let's step inside a modern rope manufacturing facility to discover the journey from raw fibers to a neatly coiled rope ready for shipment. For thousands of years, humans relied entirely on nature to produce ropes. Even today, natural fibers are still used in many applications, prized for their biodegradability, rustic appearance, and grip. Let's look at the most common natural fibers. Sisal. Derived from the long, stiff leaves of the agave plant, sisal is coarse and rigid. It's ideal for ropes that need to hold shape or resist stretching, such as in agriculture or crafts. Its golden hue and rough texture make it popular for decorative uses too. Hemp, one of the oldest rope materials in history. Hemp fibers are strong, durable, and relatively smooth compared to sisal. Hemp ropes are still used for theatrical rigging, boating, and vintage-style applications. They're also resistant to UV light and rot, a rare trait for natural fibers. Cotton. Softer and more flexible, cotton ropes are typically used indoors or where comfort matters, such as pet toys, clotheslines, or decorative cords. However, cotton is weaker than other options and not well suited for outdoor or high-load use. Coir. Made from coconut husks, coir is the roughest of natural fibers. It's highly resistant to salt water and decay, making it suitable for marine ropes, mats, and erosion control nets. Each of these natural fibers arrives at the rope factory in compressed bales, often sourced from global agricultural suppliers. Before anything else, they're you. But nature has limitations. That's where science steps in. Modern rope production now leans heavily on synthetic fibers, which outperform natural materials in nearly every category: strength, durability, resistance to weather, and consistency. Let's break down the major players. Polypropylene, PP. Lightweight and cost-effective, polypropylene is one of the most commonly used fibers in the rope industry. It floats on water, resists mildew, and is used in everything from pool ropes to utility lines. However, it has low UV resistance and tends to degrade under sunlight unless treated. Nylon polyamide, known for its high tensile strength and excellent elasticity. Nylon ropes are perfect for dynamic loads like towing, climbing, or shock absorption. They're also abrasion resistant and long-lasting, but absorb water, which can weaken the rope when wet. Polyester. Strong, low stretch, and excellent at resisting UV, heat, and chemicals. Polyester ropes are often used for sailing, winching, or industrial tasks. Unlike nylon, it retains strength when wet, making it a top choice for marine and outdoor use. Kevlar, aramid fibers, incredibly strong and heat-resistant. Kevlar ropes are used in specialized fields like aerospace, military, or fire rescue. They can handle extreme tension and temperature, but are costly and less flexible than other options. These synthetic fibers arrive at the factory in pre-extruded filaments or on large industrial spools. Everything is now set for the next stage, fiber preparation, where these raw threads begin to take shape as structured yarns. At first glance, a bale of raw fiber looks like chaos. Whether it's natural strands fresh from the earth or synthetic filaments extruded by machines, the material is loose, tangled, and shapeless. There's no strength yet, no direction, just potential.